In today's session, we will take a look at L2 contrast reduction attack, which is a type of an adversarial attack used in machine learning and deep learning models, specifically targeting the contrast of input images. This attack belongs to the family of L2 norm-based attacks, which minimizes the L2 distance, which is also called Euclidean distance between the original and the adversarial image. The primary goal of the L2 contrast reduction attack is to subtly reduce the contrast of an image in a way that the model still classifies it correctly, but often while preserving the perceptual quality of the image. Unlike traditional attacks that add noise or perturbations to the image, this attack works by altering the contrast of the image in a controlled manner to confuse the model. The L2 contrast reduction attack focuses on minimizing the contrast between pixels in an image. This reduction in contrast can mislead the model into making wrong predictions, as it diminishes important features or patterns that the model relies on for classification of the image. The attack uses the L2 norm to ensure the perturbation stays within a certain limit, ensuring the changes to the images are small and hard to detect. The images will contain the changes which the model will get affected on, but it can't be easily detected by a human eye. So let's discuss about the general steps which are involved in this attack, the L2 contrast reduction attack. Step 1 is gradient calculation. The attack will first calculate the gradient of the loss with respect to the input image. This gradient is essentially a map of how each pixel in the image influences the model's prediction. The loss function would likely depend on the difference between the model's predicted output and the true class label, such as cross entropy loss. Then comes the second step, which is contrast reduction. The core idea of the L2 contrast reduction attack is to reduce the contrast of the image. To do so, the attack would involve adjusting the pixel value such that the difference between the pixel values is reduced, making the image appear less distinct to the model. Contrast reduction can be done by applying a scaling factor to the image pixels or by subtracting the pixel values from a central value, for example like mean, to reduce their variability. Then comes the step 3, which is L2 norm constant. The attack would limit the magnitude of changes applied to the image using an L2 norm constant. This ensures that the perturbation added to the image does not exceed a certain threshold. The L2 norm, which is also called Euclidean distance, is used to quantify how much the image has been altered. In adversarial attacks, we want the changes to be minimal to avoid detection by humans, but sufficient to fool the model. So the next step is step 4, which is the optimization. In this, the perturbation applied to the image is usually optimized using an iterative process like gradient descent, in which the gradients are used to guide the adjustment to the contrast, reducing the contrast in a manner that maximizes the model's error. The next step is iterative updates, in which the perturbation is applied iteratively. In each iteration, the contrast of the image is reduced further based on the calculated gradients until a stop criterion is met, such as which the criteria can be L2 distance or number of iterations, any of it. Then comes the final step, which is step 6, in which the adversarial image is returned by the method, and which is then used for performing the attack on the model. Okay, so now let's go through the L2 contrast reduction attack class, which is present in the full box. We'll go through the original code of it, by the way, which is open source right now. So the code snippet which is visible on your screen contains a class which is called L2 contrast reduction attack, and which is subclass of a fixed epsilon attack, meaning it performs attacks where the perturbation size, which is epsilon in this case, is fixed. The goal of this attack is to reduce the contrast of the input image towards a given target value. The target is specified as a relative value, in this case, which is default 0.5, which will guide the contrast reduction, and it's relative to the bounds of the input image, usually which are between 0 and 1. Now, as you can see, there's a constructor on the screen which has an argument name target, which specifies the contrast reduction target value, of which the default value is 0.5 as it is visible on the screen. This target represents the point towards which the image's contrast will be reduced, and it is scaled between the minimum and maximum pixel values of the image. The next thing is the distance metric, which is visible on the screen. This attack uses L2 norm, Euclidean distance, as the distance metric to measure how much the perturbation changes the image. The method visible on the screen is called run, which is used to run the attack. And the inputs here represents the input image that will be attacked, and the model here represents the model on which the attack will be performed. Criterion here is not currently used in this method, but it may be used in another types of attacks. The epsilon here is the size of perturbation to be added, which controls how much contrast reduction occurs. The raise-if method visible here ensures that no extra keyword arguments are passed, which is also a kind of validation. And the ep.s tensor converts the input image into an eager.py tensor, which is a library used to handle computations in this attack. Then the verify input bounds method ensures that the input values are within the bounds expected by the model, which is usually in this case 0 to 1 for normalized images. Here you can see the minimum and maximum pixel values, which are min and max, are fetched from the model's expected bounds. The target contrast value is calculated by linearly scaling the target between minimum and the maximum values. The direction variable is computed as the difference between the target value and the current pixel values. This gives the direction in which the pixels need to be adjusted. The L2 norm of the direction is calculated, which gives a measure of how much the pixels differ from the target's contrast value. Scale is the factor that will be applied to the perturbation. It is computed by dividing epsilon by the L2 norm. The scaling ensures that the perturbation stays within the specified bound, which is the epsilon, and if it's larger than 1, it is capped to 1 then. So here we can see the application of perturbation. The perturbation is applied by adding scale multiplied by the direction to the input image, which is here represented as x. The image is then clipped to ensure that the pixel values stay within the valid bounds, which are minimum and maximum. The class then returns the adversarial image, the modified image, which is x, after the perturbation has been applied. Restore type x ensures the image is returned in its original format before it was converted to an eager.py tensor. Now we'll take a look on the attack which is being performed and its operations closely using the mathematical intuition and the formulas. In step 1, the attack reduces the contrast of the input image towards the target value. The target is defined as a percentage of the range between the minimum and maximum values of the image pixels. Let the minimum and maximum pixel values of the image be minimum pixel and maximum pixel, as you can see in the formula on the screen. The target contrast value T is calculated as the formula which is been displayed on the screen, in which the target is a fraction between 0 and 1, for which the default value is 0.5 currently. If the target is 0.5, the target contrast value is exactly halfway between the minimum and maximum values of the image. If target is 0, the target contrast is set to the minimum pixel value, and if the target is set to 1, the target contrast is set to the maximum pixel value. Step 2 is to calculate the direction of the perturbation. We calculate the direction in which we need to adjust the image. This is simply the difference between the current image pixel values, which is x, and the target constant value t, which you can see on the screen determines the direction. X here is the current pixel value of the image, and t is the target constant value calculated above. The next step is to calculate the L2 norm of the direction. The L2 norm measures how far the current pixel value x are from the target constant value t. The L2 norm of the direction is calculated as the formula which is being displayed on the screen, in which direction I represents the difference between the target contrast value and the current pixel value for each pixel. The sum is taken over all the pixels of the images. This steps gives a measure of the magnitude of change, how much contrast needs to be reduced of the image. The next step is to scale the perturbation. Now we need to calculate the perturbation so that it doesn't exceed a specified size, which is denoted by epsilon, if you remember. The scaling is calculated as the formula which is being displayed on the screen, in which epsilon is the maximum allowed perturbation size, which was declared by the attacker previously, and the direction is the L2 norm of the direction, which was calculated in the step 3. If the scale factor is larger than 1, meaning the required change is too large, we need to cap the scale to 1 then, which is done by the formula which is being displayed on the screen. This ensures the perturbation is bounded and doesn't exceed the maximum allowed size. The next step is apply the perturbation. The perturbation is then applied to the image by adding the scale direction to the original pixel values, which is how it's performed is being displayed on the screen, where the x is the original pixel value, direction is the difference between the target and current pixel value, scale is the scaling factor. This new image which is now being created has reduced contrast compared to the original image, and this will be then passed to the next step, which involves the clipping of the image to the valid range, of which the formula is being displayed on the screen, in which the minimum pixel and maximum pixel are the valid pixel value ranges, usually from 0 to 1 for normalized images. The clip function ensures that no pixel value falls outside this valid range. So the first step is to import the necessary libraries in the code. The first one is Foolbox, the second is NumPy, which is used for numerical operations, especially for handling arrays. Another is TensorFlow, a deep learning library here used to load the pre-trained MobileNet V2 model. Then you can see the MobileNet V2, a pre-trained neural network model used for image classification. The process input function ensures the image is ready for the model. PIL, the Python image library, which allows us to open, manipulate and save image files, and google.colab.files, as this code was ran on the Google Colab, and the file system of the Google Colab was used for storing the files and retrieval. Step 2 is to upload an image, where you can see the code on the screen, which allows you to upload an image file from your local system into Google Colab. The uploaded file is stored in the uploaded directory, and we retrieve the image path using the list uploaded.keys function. Step 3 is to load the pre-trained MobileNet V2 model. This line loads the MobileNet V2 model pre-trained on the ImageNet dataset, which is a large-scale image classification dataset. The model weights are loaded from the ImageNet dataset, making it capable of classifying images into 1000 different categories. The next step is to define a function to process the image. As you can see, the function opens the uploaded image and converts it to RGB mode if it's not already been converted to, or if it's not already in the RGB format. Then resizes the image to 224 by 224 pixels, which is the input size required for MobileNet V2, converts the image to a NumPy array of type float 32 in this case. The next line represents processes the input method, which prepares the image for input into the MobileNet V2 model by normalizing the pixel values of the image. The method on the below line adds an extra dimension to the start of the array to make the image shape compatible with the model's input. Therefore, it adds a batch dimension. The next step is to pre-process the image. Image np equals to pre-process image path. This line of code convert the uploaded image into a format ready for the model. Next step is to make an original prediction for the image passed. So model.predict image np. This makes a prediction on the pre-processed image using the MobileNet V2 model. The np.argmax spreads original. This line of code, this function retrieves the index of the class with the highest predicted probability. Then the predictions are decoded from the model into a human readable label, returning the top one prediction. The code then prints the original prediction class ID and the confidence score. Next step is to set up the full box model. The code visible on the screen wrap the mobile net v2 model using full box, specifying the inputs, therefore the maximum and minimum allowed pixel values for the image. Full box, as we know, expects the image pixel values to be in the range -1 to 1, so we normalize the input accordingly. The next step is to define and run the attack. fb.attacks.l2ContrastReductionAttack. This initializes the L2 contrast reduction attack from the full box. The attack reduces the contrast of the image by perturbing its pixels values in a way that doesn't visually change the image too much but misleads the model. Epsilons, here is the value represents the magnitude of the perturbation. In this case 145 is the value that will be used to scale the perturbation for the attack. The attack is run on the image using then the attack f model image np.array true label epsilons equals to epsilons, this line of code which applies the adversarial perturbation to the image and returns the adversarial image. Next is to check if the attack was successful. This block of code, which is visible on your screen, checks if the adversarial attack generated a valid result. If the adversarial image exists and is valid, the code proceeds to predict the class for the adversarial image, then decode the adversarial prediction into human readable label. Then it checks if the predicted class for the adversarial image is different from the original class, indicating a successful attack. Then it prints the adversarial prediction and whether the attack was successful. If it was, then the class ID will be visible changed. If the adversarial attack does not produce any result, it suggests increasing the epsilon value to apply a larger perturbation. And here is the output of the payload, in which original prediction, adversarial prediction and perturbation added, the three values are visible to you. The original prediction refers to the model's classification of the input image before any adversarial attack was performed on it. Tensor 845, the model prediction class ID 845, corresponding to a specific class in the ImageNet dataset, which can be banana or tennis ball or anything which it represents. Will not go in detail about that. And you can map this class ID to its human readable label if you want, using a function like decode predictions in TensorFlow. Adversarial prediction here is representing the output we got after applying the L2 contrast reduction attack. The perturbed adversarial image was fed back into the model, which gave this result. Next we see here is the adversarial prediction, which is the output we got after applying the L2 contrast reduction attack. The adversarial image was fed back into the model. The prediction is class ID 111, which is different from the original prediction, indicating that the attack was successful, as the model was not able to correctly identify the class of the image after the image was manipulated applying adversarial. The L2 contrast reduction attack, as you have seen, exposes the fragility of even highly optimized neural networks like MobileNet v2. In this case, we have seen the practical implementation of the attack on the model. I have also tried on the VGG16 and Inception v3 model, but not gonna share the payload here. The L2 contrast reduction attack manipulate the contrast and adhering to L2 norm. This attack successfully shifts the prediction without drastically altering the image's appearance. This is a stark reminder of the adversarial vulnerabilities inheriting in the deep neural networks, an exploitable gap between human perception and machine interpretation. It underlines the critical need for robust defenses in real-world applications, especially those in security-sensitive domains like autonomous vehicles, healthcare, and finance. So in the end, this attack exemplifies how adversarial perturbations are not just theoretical constructs but potent tools capable of deceiving the most advanced systems with calculated precisions. Mastering and mitigating such attacks is crucial for an advancement of AI's reliability and safety.